In this pre-lecture, we're going to review chemical equilibrium so that we're ready to go when we start to see some of these problems. So there's two big questions that happen in chemical reaction engineering. If we're given a set of reactants and conditions, if we want to know what the equilibrium concentration of the mixture is, we're talking about what's called chemical equilibrium thermodynamics. So that's trying to figure out where is the equation at equilibrium. If we've balanced out our equation correctly and we've done everything that we should stoichiometrically, what's going to happen at equilibrium, right? That's what a lot of chemical engineers are worried about. That's what a lot of chemists are worried about. We can also take a look at how long will it take the system to reach equilibrium, and this is called chemical kinetics. And this is something that's going to be a little bit more critical to us as environmental engineers because many times equilibrium becomes synonymous with steady state. Not every time, but some kind of an equilibrium is going to equate sometimes towards where our steady state is. So figuring out the amount of time sometimes is important for us as we go forward. So there's two ways of talking about chemical equilibrium. Finding the chemical equilibrium concentration, and then the time it takes to reach chemical equilibrium. So some other concepts that I want to make sure that we review are things like irreversible reactions. So these are reactions that only proceed in a single direction. And this can actually happen quite commonly in a lot of our industrial processes where we can't go backwards and we can't have an equilibrium between the two. There's just a reaction that happens. And in an irreversible reaction, the concentration of the limiting reactant will eventually equal zero. We're going to consume all of that limiting reactant. Now, we could have some amount of that excess reactant left over, but we're going to completely consume that limiting reactant in an irreversible reaction. Reversible reactions are where the reactants form products and the products can also form reactants, right? So that's when we have the arrows going both ways in a chemical reaction. So chemical equilibrium is going to occur when the rate of reactions between the products and the reactants does not change with time. So many times we like reversible reactions in chemical engineering or environmental engineering, but sometimes we only want irreversible reactions. So there's going to be scenarios where it's better to have reversible or irreversible, depending on what type of industrial process we're designing. The other concepts that I want to talk about are what happens when we have multiple reactions, and then these two concepts called yield and selectivity. So although we might want some specific reactions to give us specific products, many times those reactants don't do the things that we want them to do, and they don't do the things that we want them to do because other side reactions are occurring, right? So in the real world, we have a lot of times we have trouble making sure that the reactions are proceeding without interference with other reactions or with other things that are in the environment. So that's important to remember. So side reactions are going to occur. That's going to lead to economic losses. So it becomes more costly and complicated to achieve our desired result. So we try to minimize side reactions most of the time. And then yield and selectivity are two different concepts that describe the degree to which we get the desired reaction predominating. So we want high yield and high selectivity values. So we might have two reactions occurring, for example, and we really want reaction 1 to predominate and give us a high yield or a high selectivity. And that side reaction 2, we want to make sure that that's not a competing reaction that's going to dramatically decrease what we're getting out of our production of our reactions. So let's talk about yield and selectivity in a little bit more detail. I apologize, one of my transitions didn't work here, but let's talk about yield first. So yield is the moles of desired product formed divided by the moles formed if no side reactions occur. We multiply that fraction by 100%, so yield is represented as a percentage. Selectivity is slightly different. Selectivity says the moles of desired product formed divided by the moles of undesired product formed. So selectivity is a ratio of the moles of A to the moles of B, where A and B are both different species. So yield itself is looking primarily at 100% consumption of the limiting reactant, right? So that's what that denominator is representing, right? The numerator is the same in both yield and selectivity, but in yield, the denominator is related to 100% consumption of the limiting reactant. In selectivity, The selectivity it's a ratio basically of A relative to B or B relative to C or whatever that happens to be in the system. So these are going to be some concepts that we're going to start to see when we start to see multiple reactions in our systems. So just make a note, take a pause if you need to, that yield and selectivity have the same numerator, but they have different denominators. They are both measurements that look at the amount of production of the thing that we want, but they look at it in a slightly different way.